In section 5.2, we look at systems of linear equations in three variables. Basically, the situation here is the same as in the previous section, except now we have three variables. So you see in this example here, we have x, y, and z. And we also have three equations, usually. Now, this first example is a really simple example. And it's simple because you'll notice that the first equation has all three variables. The second equation is missing the x variable, and the third equation is missing both the x and the y variable. So when we're looking for the solution here, we're looking for the values of x, y, and z that satisfy all three equations. Well, we can see from the last equation that we know z equals 2, right? So this is part of our solution. And because z is equal to 2, you can take this value of z and you can plug it into the equation that comes before it. If you do that, you get y plus 2 is equal to 0. Subtracting 2 from both sides tells us that y must be negative 2. So now we know z equals 2, and we also know y equals negative 2. We can take each one of these solutions and substitute it back into the first equation. And if we do that, we get x plus negative 2 minus 2 is equal to 10. And this is x minus 4 equals 10. And if you add 4 to both sides, you get x equals 14. So our solution is z equals 2, y equals negative 2, and x equals 14. And you can write that solution as an ordered triple. And the way we do that is we write x first, y second, and z third. And so our solution would be written as 14, negative 2, positive 2. So the question is, when you're given a three-variable system where all three variables are present in all three equations, how do you solve that? In other words, how do you get it to this very nice format where you're missing a variable in each of these successive equations? Let's talk about the process. When solving a three-variable system, or actually any number of variable system, there are three things that you are allowed to do in the process of solving. The first thing you are allowed to do is interchange two equations in the system. So for example, here you can see that we have three equations. If we want to change the first equation to be either of the other two equations, that's no problem. We can do that. Another thing you can do is you can multiply one equation in the system by a non-zero constant. So I can take any one of these equations and multiply both sides by any non-zero number. And the third thing, and probably the most important thing, is you can multiply one equation in the system by a non-zero constant and then add the result to another equation in the system. Now, if you remember back in the first section of this chapter, this is pretty much what we did when we used elimination to solve two variable systems. So let's go ahead and go through this particular example. And this process that we're about to use is called Gaussian elimination. So the first thing that I want to do here is I'm going to write the second equation here. I'm going to write that in the spot of the first equation. And the reason I like that equation better for the first equation is because the coefficient of x is 1 here. So our first equation will become x minus 2y plus 2z is equal to negative 1. And then the first equation up here, I'm going to write in the second spot. So that becomes negative 2x plus 2y plus z is equal to negative 6. And the third equation remains unchanged. Now remember, what we really want to have happen here is we want this x variable here to be missing, and in the last equation we want both of these variables to be missing. So what I'm going to do here is use the first equation to get rid of the x in the other two equations. And I'll have to do these in 2 steps. Now for reference, for the rest of this problem, I'm going to number these equations so that we can talk about first equation, second equation, third equation. So this is the first equation, this is the second equation, and this is the third equation. So what I'm going to do here is I'm going to multiply equation number 1 by 2, then add that result to equation number 2. So let's go ahead and go through that process. So here we have the first equation. I'm going to multiply that by 2 on both sides. And then I'll get that result. And so multiplying by 2 gives us 2x minus 4y plus 4z is equal to negative 2. The second equation is unchanged. And then I'm going to add those together. And when I add those together, you can see that the x variable cancels out. So we end up with negative 2y plus 5z is equal to negative 8. And we'll save this result. Now what I'm going to do is the same step, but with the first equation and the third equation. So I'm going to multiply the first equation by negative 3 and then add it to the third equation, and that will get rid of the x here. So that's what I have here. The first equation is being multiplied by negative 3, and I'm adding that to the third equation here. So let's go ahead and do the math on this. So negative 3 times x is negative 3x. Negative 3 times negative 2y is positive 6y. And negative 3 times 2z is negative 6z. And that's equal to positive 3. The last equation is unchanged. And now I'm going to add these together, and once again the x variable will cancel out, and we get 8y minus 7z is equal to 6. So now what I'm going to do is I'm going to take that first equation, rewrite it, and then I'm going to take this equation here, and that's going to replace equation number 2, and this equation here will replace equation number 3. So from here I get sort of a new system. So we have x minus 2y plus 2z is equal to negative 1. We have negative 2y plus 5z is equal to negative 8. And we have 8y minus 7z is equal to 6. So the next step now is I want to get rid of the variable y in the last equation. To do that, I'll use only these two equations. I'm going to multiply this second equation by 4, which will change this to a negative 8y, and then I can add it to this equation. So if we do the math on this one here, we're multiplying that second equation right here by 4. That is going to give us negative 8y plus 20z is equal to negative 32. And the other equation is unchanged. And if we add these together, you can see that the y's are going to cancel out. And we will end up with 14z is equal to negative 26. Oh, sorry, that's 13z, not 14z. Right? 20 take away 7 is 13z. And then from here, if you divide that by 13, this leads to z equals negative 2. All right, so this is our new third equation. So now what I want to do is write this whole system here once again, but I'm going to replace that third equation with z equals negative 2. So let's go ahead and write that over here. Now we have the system in the format that we want. Notice that it steps down just like we had in that first example. So we know that z equals negative 2. This is finished. But then we can take this value of z and plug it into the equation right above it to get negative 2y plus 5 times negative 2 is equal to negative 8. And this is negative 2y minus 10 equals negative 8. Adding 10 to both sides gives us negative 2y is equal to positive 2. And then dividing by negative 2, we get y is equal to negative 1. And now once we have these two values, I can take the value of z equals negative 2 and plug it into the first equation. Take the value of y equals negative 1 and also plug it into the first equation. And that gives us x minus 2 times negative 1 plus 2 times negative 2 is equal to negative 1. And this is x plus 2 minus 4 equals negative 1, or x minus 2 equals negative 1. And finally, adding 2 to both sides, we get x equals 1. And so our solution here, once again, is the ordered triple x, y, z. And that solution is x equals 1, y equals negative 1, and z equals negative 2. So you'll notice that the process is pretty arduous, right? It's a long process, it's a tedious process, but you just have to move slowly and you have to be very careful not to make simple mistakes. Now let's take a look at an example of a system with infinitely many solutions. All right, now you're going to get infinitely many solutions very often when the number of equations is less than the number of variables. To get exactly one solution, you have to have at least the same number of variables and equations, and we don't have that here. Now we can go ahead and go through the same process. So I'm going to rewrite our system, and we're going to attempt to do the same thing we did in the previous example. So what I would like to do here is get rid of the 5x. To do this, I am going to multiply the first equation by 5 and the second equation by 3 so that we get a common coefficient here. We'll have a negative 15x and a positive 15x. So let's go ahead and do that. So if we do the math on this, we get negative 15x plus 5y minus 10z is equal to 5. And the second equation becomes positive 15x minus 3y plus 12z is equal to negative 3. And if we add these equations together, the x variable cancels out, and we get 2y plus 2z is equal to 2. And now we have a new system where the first equation is the same. So notice that we don't change the first equation. We are just using the first equation to change the second equation. And that second equation now is 2y plus 2z is equal to 2. And you'll notice that we can't continue any further like we did in the previous example. So from here, what I'm going to do is let z be equal to some variable. I'm going to call that variable t, which is often referred to as a parameter. You don't have to worry too much about this. I just want to bring it up. If z is equal to t, then if you plug z equals t into here, you get 2y plus 2t is equal to 2. And I could solve for y by subtracting 2t from both sides. And then I can divide everything by 2 here. And if I do that, I get y equals negative t plus 1. So we said let z equal t. Now we see that y is negative t plus 1. Now we can take each one of those and plug them back into the first equation, and that will give us negative 3x plus y, which is negative t plus 1, minus 2 times z, which is t, is equal to 1. And this is negative 3x minus t plus 1 minus 2t equals 1. And that's negative 3x minus 3t plus 1 equals 1. Subtracting 1 from both sides and adding 3t to both sides gives us negative 3x is equal to 3t. And finally, dividing both sides by negative 3, we get x is equal to negative t. So what I've done here is I've expressed the solution in terms of this third variable t, and now we can see that x is negative t, y is negative t plus 1, and z is t. And that means your solution is negative t plus 1, and t. But what is t? Well, t can be any real number. There's no restriction on t. So for example, if t is equal to 0, if you plug in 0 here, you get 0, and then you get 0 plus 1 is 1, and you get 0. So that would give you the point 0, 1, 0. So this is a solution to the original system. But there's infinitely many solutions because I can let t be equal to any value I want. So for example, if t is equal to 3, the solution is going to be negative 3, and then here, negative 3 plus 1 will be negative 2, and then negative 3. This is also a solution. And you can verify this by taking these values of x, y, and z and plugging them into the original equation that you got. And we can do this indefinitely. So I can pick negative 2 for t. If t equals negative 2, we get negative 2 is 2. Then we get 3, and then we get 2. This is another solution, right? And so again, we could keep doing this forever. And this is why this problem has infinitely many solutions. Now, one thing I wanted to mention is that in your textbook, they don't introduce the concept of a parameter. What they do instead is, rather than calling z a parameter t, they just let z be z, okay? So they just say z is itself. And then if you solve for y in terms of z, you get 2y plus 2z equals 2. Solving for y, you get 2y equals negative 2z plus 2. And then dividing by 2 on both sides, you get negative z plus 1. And then if you plug both of those in the first equation, you will find that x is equal to negative z. So they let z be z, y will be negative z plus 1, and x will be negative z. And if you do this, your solution will be negative z plus 1, and z. But I want you to understand, if you look at this carefully, right, this is the same as what we got here. It's just that over here, instead of calling z itself, we gave z a new name. We just called it t, right? But this solution here is the same as this solution over here. It's just a matter of whether you choose to use a third variable, or rather a fourth variable, t, which we call a parameter. And this is typically how it's done in a linear algebra course, but you could do it either way. In the next example, we look at a system of equations with no solution. Now, when you're looking at this system in the beginning, there's no way to really know for sure right away that it has no solution. So that means that when you're solving this system, something must happen in the process that gives you no solution. So let's go ahead and take this system, and we will do the same thing that we did in the previous examples. So I am going to get rid of the x variable in the second equation and get rid of the x variable in the third equation. To do this, I am going to multiply the first equation by negative 3 and then add it to the second equation. And when we do that, we get negative 3x minus 3z is equal to negative 9. And that second equation is 3x plus y plus 2z is equal to 0. Adding those together, you can see the x variables cancel out, and we get y minus z equals negative 9. And then we're going to do the same thing for the first equation and third equation. So I'm going to multiply this first equation by negative 4 and then add it to the third equation. And when we do this, we get negative 4x minus 4z equals negative 12. And the last equation is unchanged. And when we add these together, the x variables cancel out. And we end up getting y minus z is equal to negative 7. So now we take this equation, this is our new equation number 3, this one, which is our new equation number 2, and we keep our original first equation, and we'll write all those down to get the following system. And then we go through and we do the next step. And the next step is we get rid of the y variable in the last equation. This is pretty simple to do. We can multiply the second equation by negative 1 and then add it to the third equation. And so if we do that, multiplying here by negative 1, that's going to give us negative y plus z equals 9. And then the last equation is y minus z equals negative 7. And when you add these together, you'll notice the y variable cancels out and the x variable cancels out, which means we have 0, but on the other side we have 2. And this is a false statement. As soon as you get a false statement, you can immediately say that this system has no solution. So this is what will happen when you have no solution, is the variables will cancel and you'll end up getting a false statement. Our final example here is an application of 3 variable systems. It says the graph of the function f of x equals ax squared plus bx plus c is a parabola that passes through the points negative 1, negative 3, 1, 1, and negative 2, negative 8, where a, b, and c are constants to be determined. So what we want to do here is we want to find the function f of x equals ax squared plus bx plus c. So that means we want to solve for a, b, and c. To do this, we're going to think about what does it mean for a point such as negative 1, negative 3 to be on the graph of this parabola. Well, remember, negative 1, negative 3 implies x equals negative 1 at the same time that y equals negative 3. Or we can say x equals negative 1 at the same time that f of x is equal to negative 3. So if I plug in negative 1 for x, then I get negative 3 for f of x. That gives me an equation. And that equation is here. So f of x is negative 3 when x is negative 1. That gives us negative 3 equals a times negative 1 squared plus b times negative 1 plus c. So all I did here, again, is I replaced x with negative 1, and I replaced f of x with negative 3. This gives us negative 3 equals a times negative 1 squared is 1, plus b times negative 1 is minus b, and then plus c. So I'm going to keep this for now. Now what I'm going to do is do the same thing with these other 2 points, right? So for the point 1, 1, we're going to plug in x equals 1 at the same time that f of x is equal to 1. And so if you do that, you get 1 is equal to a times 1 squared plus b times 1 plus c. And that gives us the equation 1 equals a plus b plus c. So that's our second equation. And then if we do it one more time, we can do it with this point, negative 2, negative 8. That means when x is replaced with negative 2, f of x is replaced with negative 8. And if we do that, we get negative 8 is equal to a times negative 2 squared plus b times negative 2 plus c. And that gives us the equation negative 8 equals 4a minus 2b plus c. So you see what we've done here is we have created a 3-variable system. I now have 3 equations and 3 unknowns. So let's go ahead and write these 3 equations together like a system. So here is that system. So I've just taken each one of these equations here and I wrote them vertically. And now I'm going to do the same thing that we have been doing. Now I didn't show my work here, but what I'm doing here is I'm multiplying this first equation by -1, and then I'm adding it to the second equation. That will cancel the a. -1 times this is a b, plus b is 2b. -1 times c is -c, plus c is 0. And -1 times this is 3, plus 1 is 4. And then for the last equation here, what I did is I took this first equation, multiplied it by -4, and then added it to the last equation. So if you want, I encourage you to pause the video to make sure that you can get these particular equations. Now from here, I'm going to multiply this second equation by -2, and I'm going to add it, I'm going to multiply by -1, and I'm going to add it to this equation to cancel the b here. And if I do that, I get the following. So again, you should verify that. I just multiplied this by -1, and I added it to this. And now we can easily solve for a, b, and c. So you can see in that last equation, -3c equals 0. Dividing by -3, we can see that c is 0. In the second equation, we have 2b equals 4. Dividing by 2, we get b equals 2. And in the first equation, we have a minus b, which is 2, plus c, which is 0, equals -3. So this is a minus 2 equals -3, or a equals -1. So I have my solutions for a, b, and c. A is -1, b is 2, and c is 0. And if I come back to the original equation, I can plug those in to determine the function f of x. So f of x is ax squared, but a is -1, so that's -1x squared, plus, and then it's b times x, but we know b is 2, so it's plus 2x, and then plus c is 0. So our function f of x should be -x squared plus 2x. That should be the parabola that passes through these 3 points. Now, let's bring in a graph to make sure this is what happens. So here is the graph of the function f of x equals -x squared plus 2x. That's this graph here. And you can see that it does pass through the point 1, 1. It passes through the point -1, -3. And it also passes through the point -2, -8, as prescribed in the original problem.